Okay, this will be part 3 of chapter 16 to get us ready for the quiz and the test. The other day we didn't go over pumping loss very well. So pumping loss is a gasoline engine problem because gasoline engines limit the amount of air in to the engine to control engine speed. So they have a throttle plate, and having that throttle plate somewhat restricts the air being drawn into the cylinder on a gas engine. So this is referred to as pumping loss. It's not a pressurized manifold like a diesel engine has with the turbocharger and whatnot. So anyway, that's what pumping loss is. It's just a gasoline engine thing. Remember, on a diesel engine, we regulate fuel to control engine speed, and we don't really care how much air goes to it as long as we get enough. In fact, we get about 200% more air than we need going through a diesel engine. Gasoline engine, you regulate the amount of air to control engine speed, and then you tailor the fuel for that much air. So that's the difference between the two. So we don't deal with pumping loss on diesel, it's just gasoline engines because of the throttle plate. Just wanted to go back and reiterate that because I didn't do a very good job the other day. Now we're going to pick up where we left off with injection timing. Just remember that injection timing affects emissions. That's why the late model engines have much better emissions. With the use of all the computers and not having to rely on the camshaft to control somewhat when fuel is injected and whatnot. So now we have better control of that. So we can reduce smoke. And by that I mean a modern diesel engine, anything after basically 2007, we should just see like kind of a heat wave coming out of the tailpipe. If we see black smoke, that's unburnt fuel, so that is particulate matter and soot that causes that. So we shouldn't see any black smoke, and of course blue smoke is burning engine oil, shouldn't see that. White smoke is either incomplete combustion, so cylinder misfire, or steam from coolant getting into the exhaust. So basically we should see no exhaust coming out, other just kind of a heat wave looking coming out of the exhaust. Finer atomization shortens ignition timing delay, and timing can be retarded to reduce emissions. So with electronically controlled, we were able to roll the timing back or retard it to help reduce emissions. But by doing that, we had to have a higher injection pressure. That's why common rail is kind of taken over, because we can inject the fuel at a lot higher pressure and have a lot better atomization, so the fuel burns completely and it doesn't like kick back, because we had a lot smaller window with the mechanical injection on our timing. So it's allowed us to address our emissions issues a whole lot better. Okay. Rate shaped injection just means that back in the old mechanical days, we gave it the amount of fuel it needed in one big shot. So it kicked on the piston pretty hard. You had a lot noisier engine, especially at idle. The diesel engines now are a lot quieter because we can have up to 7 different injection on common rail systems. The old HEUI we used before this one, the first generation, it had 3 injection events, but we're up to possibly 7 if needed on our common rail now. So what that allows us to do is tailor the fuel through the complete cycle, and instead of giving it too much at the front and hoping it all burns up at the end, now we can give it in little pulses and follow all the way through the cycle and try to tailor the injection event for fuel economy, power, and emissions. Mechanical rate shaping: as the nozzle opens, injection rates increase, reducing noise and lowering emissions. HEUI injectors, like I said, can produce 2 to 3 injection events, but pretty much everything is common rail now, so we're up to 7. So the first one we have is a pilot injection. So if you could imagine, if I had a small fire burning and I put some more fuel on it, it's going to be more of a controlled ignition of that fuel. Whereas if I just threw a bunch of fuel on some coals and just let it kind of explode. So what pilot injection does is gives it just a little bit of fuel and starts a small burning process, so that when my main injection pulse comes after that, there's already kind of a fire started, and it makes it a little bit more smooth. It increases performance, minimizes oxides of nitrogen and noise, and a small quantity of fuel is delivered a few degrees before the main injection, so that's what pilot injection is. So now if you look, we have a couple of pilot injections to get everything started. Then we have main injections to keep it going. We hit our peak, drop off, and then we have these little post-combustion injections. And what the post-combustion injections do is add a little bit of heat to the exhaust to burn up any, or to the cylinder to burn up any soot that's left over in the cylinder. So we give it just a little bit more fuel right at the very end. They're very small pulses, but they basically eliminate the soot, or help eliminate it, and cut down on the unburnt fuel coming out the exhaust, so it's less for the diesel particulate filter to have to take care of. Okay, so that's post-combustion injections. What I just said adds more heat, reduces hydrocarbons and soot. So fuel atomization is the breaking up of fuel droplets into very small droplets. Finer atomization means fuel ignites sooner and burns faster and more complete, so that's why our injection pressures have went as high as they are, and they keep looking for ways to increase that even higher to get the emissions better. The finer you atomize the diesel, the quicker it ignites and the more it burns completely up. So fuel droplet size and particulate matter emissions. Fuel droplets result in complete combustion and less particulate matter on fine droplets. Particulate formation, black or gray smoke indicates excessive particulate matter caused by large fuel droplet size, poor mixing of air and fuel, inadequate pre-ignition temperatures, or inadequate combustion time. Can also be like a dribbling injector that's leaking. So distribution of fuel into the combustion chamber is key to the performance. Trying to get the fuel distributed better so it can mix with the oxygen molecules and have a more efficient burn. So the newer injectors can have up to 13 tiny little holes in the tip of their injector, where old injectors had 4 or 5 holes. So we've got a lot finer and better distributed fuel mist. Okay, injection lag. Now, this confuses people because you would think injection lag is going to be timing with a lag thing, which it is, but injection lag is the time delay between the start of fuel pressurization and the moment fuel injection starts. So really long old fuel lines, distributor pump time, we had injection lag because the fuel lines actually swell a little bit with the increased pressure, so that slows everything down. You had to overcome a lot farther distance, so they were prone to more lag. A unit injector had very little lag because the fuel is pressurized inside the injector, so we didn't have any kind of line or anything like that to swell or a long ways to go before the injector started to open. So just think of injector lag as the time you build pressure versus the time it starts actually spraying out the tip. So common rail is not as bad as the old distributor type pump, but it has a small amount of lag. So but anyway, it's not really causing us a problem. Now if we move on to Electronic injectors like the common rail use a magnetic actuator, have a little bit of lag caused by the time it takes for the current to build in a magnetic field, but electricity is pretty fast, so it's minimal. Okay. One last thing we need to hit that might show up on the test is the old mechanical injection, like the distributor pumps, the inline pumps. We had to do a little timing on those, and the maximum they could have is they had to be within 2 degrees on their actual timing. So most of those pumps had just a little bit of adjustment where that you could advance or retard the pump just a little bit to compensate for the timing marks being just a little bit off with their tolerance and whatnot. So just remember that on those old mechanical ones, 2 degrees was the maximum we could be off on our ignition timing. And that should pretty much wrap it up.